Welcome back to this introductory lecture on set theory. In this fourth and last segment, we will introduce a couple new concepts, but the most important one is the Cartesian product, which is basically the product of two sets, and it's named after René Descartes, the French philosopher and mathematician. But first, let's introduce an intermediate concept that we need for the Cartesian product, and that is the concept of a tuple, or an n-tuple. It's an ordered sequence of n elements. So the main difference between a tuple and a set is that the order in a tuple matters. And in terms of notation, notice a tuple is written between parentheses, not curly braces. That's another difference with a set. Otherwise, the elements, both in tuples and sets, are separated by commas. So just remember, in a tuple, the order matters. In a set, the order doesn't matter. Now, an n-tuple has n elements, where n can be any integer from 1 up. Of course, an one tuple is just a sequence of one element. That's not very interesting. So let's consider a two-tuple, and the special name for these tuples is pairs. So a pair is just a tuple of two elements. So for example, the pair b comma 10 has b as a first element and 10 as a second element. The pair 10 comma b has 10 as its first element and b as its second element. And remember, those two pairs are different because in pairs, like in tuples, the order matters. And also remember that the set 10 comma b, indicated here by braces, is definitely not the same as either one of these pairs because a set is not a pair. Please keep that in mind. So in a tuple, the elements are identified by their position in the tuple or in the sequence. What this means in particular is that it's perfectly okay to have the pair b comma b, where the element b appears more than once in the pair, because this b is the first one and it's definitely different from the second one, which appears in position 2. Whereas if remember, in a set, it doesn't make sense to have the element b appear more than once. Okay, so now that we're comfortable with the concept of a pair, by the way, a three-tuple is sometimes or usually called a triple, and in general we deal with n-tuples. Now we can introduce the concept of a Cartesian product. By definition, the Cartesian product applies to two sets, say S1 and S2, and it's written as the multiplication of those two sets. And by definition, the Cartesian product of S1 and S2 is the set of all pairs A comma B, such that the first element in the pair A belongs to the first set S1 and the second element B in the pair belongs to the second set S2. So to be clear, the Cartesian product is a set, and the elements in that set are pairs or tuples. So now we're combining the concepts of sets and tuples. So the Cartesian product is a set of tuples, not a tuple of sets. So the mathematical notation for this English definition is the following. S1 Cartesian product S2 is by definition the set of all pairs A comma B, such that A is an element of S1 and B is an element of S2. Make sure you're comfortable reading that set builder notation by now. So let's look at an example. Let's say S1 is the set containing the two people Jane and John, and S2 is the set containing the letters A, B, C, D, and F. Remember, to build the Cartesian product, you need two sets. These two sets do not have to contain elements of the same type. Now, what is the Cartesian product of S1 and S2 in this particular example? Well, remember, it's a set and each element of that set is a pair where the first element is either Jane or John, and the second element is one of the letters in S2. So you have to consider all possible such pairs and write them down in any order to make up the set S1 Cartesian product S2. And here it is: Jane A, Jane B, Jane C, Jane D, Jane F. That's the first half. It's a set of pairs where the first element in the pair is always Jane. And now, of course, we have another set of pairs where the first element is John, with all possible elements of S2 as the second element of the pair. John A, John B, John C, John D, and John F. And that is the Cartesian product of S1 and S2. Now, this is a good time to remind you of the importance of the binding contracts that the definitions embody, and the importance as well of the notation that are associated with these definitions. You got to get it all right. So, for example, a tuple is denoted by a pair of parentheses in which the elements are separated by a comma, whereas a set is denoted by a pair of curly braces and its elements are also separated by commas. Get any one of these symbols wrong or forget any one of them and you get the wrong answer. So please be very careful about not only the definitions that you should know, but the notations. Now, we're comfortable with the definition of the Cartesian product, so the next obvious question is, what is the size of the cardinality of the Cartesian product of S1 and S2? In other words, how many distinct pairs can you build out of S1 and S2? Please pause the video and figure out the answer for yourself. Okay, you got it? That's right. The cardinality of the Cartesian product is the product of the cardinalities of the two sets S1 and S2. Let's make sure this works on the example. The cardinality of S1 is 2. The cardinality of S2 is 5. 2 times 5 is 10. And that is indeed the cardinality of their Cartesian product. So make sure you understand, even if you can prove it now, but at least understand intuitively why this formula does work. Now, of course, in the definition of a Cartesian product, nothing prevents S1 and S2 from being the same set. But when they are different, as we emphasized already, the order matters. So S1 Cartesian product S2 is not the same as S2 Cartesian product S1. Just keep that in mind for the next definition, which says that a relation from the set S1 to S2 to another set S2 is a subset of the Cartesian product of S1 and S2. Notice there's a direction here. The relation is from S1 to S2, not from S2 to S1. That's why the order of the Cartesian product matters here. So a relation is a set. And which set is it? It's any subset of this one, which we just defined. So let's consider the same examples for S1 and S2. What would be a relation from S1 to S2? Well, here is an example here. This is a set with two elements, each of which is a pair, and each one of these pairs appears in a Cartesian product of S1 and S2. Therefore, this is definitely a subset of the Cartesian product of S1 and S2, and therefore this is definitely a relation from S1 to S2. So, this is a formal definition, but what is a relation from S1 to S2? It's basically a mapping from the elements of the first set to the elements of the second set. For example, you could think of this relation as the grades for the students in a class. So the grade of Jane is A, the grade of John is B. That's an example of a relation from the set of students to the set of grades. Now, to conclude this segment, I want to extend the definition of the Cartesian products to n sets, not just 2. So, the Cartesian product of n sets S1, S2, dot, 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 Sn, which is denoted by this product here, again the order matters here, is the set of all n tuples of this form, A1, A2, dot, 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 An, such that every element in the pair belongs to one of the sets. Namely, the first element here belongs to S1, the second to S2, and the last one to Sn. So the Cartesian product of n sets is just an extension of the Cartesian product of 2 sets. So its mathematical definition is very similar, and I hope you can read that set builder notation very fast now. It says the Cartesian product of S1, S2, dot, 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 S1 is the set of all n tuples such that the first element of the tuple is an element of S1, the second element of the tuple is an element of S2, and dot, 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 the last element of the tuple is an element of Sn. So we might use that notion of a Cartesian product for 3, 4, or more sets. I just wanted to define it here, and this will conclude our lecture on introductory concepts of set theory.